Hello, everyone. My name is Hannah Turner, and I'm the president of the Marshall University Astronomy Club, MUAC. I thank you all for joining us for our Fall 2024 Virtual Speaker Series. Drawing inspiration from our sister organization, the Society of Physics Students, or SPS, which utilizes their series to spread science knowledge to the public, MUAC has created this series with the intent of capturing a glimpse into the minds of astronomers from our surrounding communities. A fundamental goal of MUAC has been and always will be to encourage astronomy discussions among upcoming generations. When we provide a platform for such knowledge to flourish, we aid a sense of possibility to all children within our local communities. Becoming an astronaut, an astrophysicist, or even a leader of a university astronomy group doesn't seem so impossible. I speak for all leading MUAC members when I say that we are very proud of what we have accomplished with this club. MUAC advisor Dr. Sean McBride could not join us this evening due to giving a talk at a face-to-face conference. He does, however, extend a sincere apology to our speaker, who we have been all very eager to hear from. With that being said, Dr. Laura Stapleton, a professor within the MU Mathematics and Physics Department, has graciously joined us in Dr. McBride's absence.
Thank you, Hannah. As Hannah mentioned, I'm Laura Stapleton. I teach in the mathematics department, and I wanted to first thank Hannah for all her efforts. She has done such a fabulous job with the club and getting this series together, not only scheduling the presenters, but also figuring out the software. So really, she is the heart of the astronomy club. So I just wanted to give her a shout out for that. But to tell you a little bit about Marshall, the astronomy club is tied to the mathematics and physics department, where Dr. McBride is the faculty advisor. And our department is really a home to a vibrant community of scholars who are passionate about exploring the fascinating intersection between mathematics and physics. Now, we have about 20 faculty in the mathematics department, and we have 8 in the physics department. And our undergraduate programs include mathematics, a BS, physics, a BS, statistics, BS. We have a graduate mathematics, which is a master's, a physical and applied science, and a physics master's. But we really consider ourselves just the right size university. We have an excellent student-to-teacher ratio of about 17-1, and our average undergraduate class sizes are about 20 students, which really, as a faculty member, it allows me to get to know my students very well. And our average graduate student class size is about 10 students. We have almost 8,300 undergraduate students, about 2,400 graduate students, and about 500 students in our professional programs. About 86 of our faculty hold a terminal degree in their field, and we would love it if you are interested in finding out more about Marshall, to either get in contact with myself or Dr. McBride. And if we certainly don't know, then we will get you in contact with the person that's the right fit for your question. But to let you know my email address, it's stapleto, STAPLETO, at marshall.edu. And Dr. McBride's email is mcbrides at marshall.edu. And if you're interested in tonight's talk, please connect with the speaker. I'm sure he would be more than happy and willing to correspond with you via email or other means. And with that, I turn it back to Hannah.
Very well said. Thank you. So without further ado, it is my most pleasure to introduce our sixth and final speaker in this series, Dr. Isaac Shlosman, who will be speaking to us this evening on seeding massive black holes at the dawn of the universe. This talk will span 45 minutes approximately, followed by a 15-minute Q&A period for all of our listeners to send questions within the live chat. We do ask that everyone hold their questions until the end. Dr. Shlosman.
Okay, hello to everybody. And thank you very much for the invitation. So as you've been told already, I will talk about how to make black holes in the morning time of the universe. And there will be a lot of new definitions, which I will try not to jump over, but to explain. But if there are questions, I would be happy to answer them. And I was told that most of the questions will be at the end. So let's start this talk. And I would start with the point of explaining what is black hole. In fact, it's very easy to explain. A black hole is not an object. It is a volume in space from which nothing can escape, even light. And light moves with the maximal speed of 300,000 kilometers per second. So if it cannot escape, then nothing else can escape. Black holes are one of the simplest objects in the universe, but at the same time, the most difficult to research. You see this sketch of a black hole. It has three ingredients. It has what is called event horizon. This is the point of no return. If you wander inside the event horizon, it is a one-way ticket and you never come back to our universe. Then there is a size, a radius of the black hole, and the central singularity. That's where the mass of the black hole apparently is concentrated, and about which we know very little. Not even some people dispute even if, that it exists. Nevertheless, these 3 points defined a black hole. Here is in the middle is a sketch of done by Kip Thorne, a Nobel laureate of 2017, who devoted his life of studying black holes and gravitational waves. And what you see here is basically a region in space. Then if you fall into this, and that's apparently Kip Thorne himself who falls in, if you reach the horizon or the event horizon, from inside you cannot communicate to anything which is outside. And then there is the central singularity. We have an image of black holes thanks to the New Horizon telescope in the nearby galaxy of called M87. That's the telephone number of this object. You see the black hole is dark spot at the center, and you have some light outside that is based on the material that falls into black hole, is squeezed, heats up, and emits light. Now, what is important for us when we talk about black hole is how massive they are. There are two groups of black holes. First, between 1 to 40 solar masses. These are apparently remnants of stellar evolution. And then there is a completely different group between 1 million to maybe 10 billion solar masses. This is what we call a supermassive black holes. And as you see, there is a gap in these masses. There is nothing in between. And this is one of the big questions. Why there are no black holes, for example, of 10,000 solar masses or 100,000 solar masses? So I put this question, big question, $100 question, why? A little bit of history. The idea of black hole, that you have an object that you cannot escape from, was first delivered in the public lecture by John Mitchell of England at the Royal Physical Society. He was actually a priest. And then put in the book by Pierre Laplace in France in 1795. In the second edition of his book, Laplace removed any idea about this object, and we don't know whether he stopped to believe them or not. This is a present quarrel between French and British historian. Then, of course, everything is based on Albert Einstein's theory of gravity that was published in 1915. And Karl Schwarzschild, who first defined it as a region of no escape and singularity and event horizon. And the word black hole was used only in 1967 by John Archibald Wheeler, and it stuck. So we call these objects now black holes. These are very strange objects. They are always hungry. And if there is nearby a star or something, they are completely ready to swallow it, as you see in this artist presentation. What is important also in these black holes, that they not only swallow everything, but they emit radiation, and they emit what we call relativistic jets that you see in this animation. So they are quite anisotropic, so in the sense that they emit in the collimated direction, in the specific direction, and they always come in pairs. If we talk about black holes, we can define the so-called active galactic nuclei, because the black holes, the supermassive black holes, always sit in the middle of galaxies, as we call them AGN, active galactic nuclei. So what you see here, a black hole, and what is called accretion disk, meaning acquiring additional mass by accretion, which is simply collecting it by gravity. So that is a simple sketch of what is called active galactic nucleus. Now, most importantly, and that's why we talk, the supermassive black holes, so as I will call them SMBH, supermassive black holes, are ubiquitous in the universe. Typically, one per present-day galaxy. And I would like to show this ubiquity in this particular sketch. So we know that black holes form very early in the stage of the universe, and today every decent galaxy has them, including the Milky Way. And so the question is, how to make these supermassive black holes, and how to make them early in the history of the universe. That is a particular slide where I want to explain the time sequence, the evolution of our universe. It started with Big Bang, and that is at the top. Okay, so that is the time zero in the age of the universe. We are at the bottom, and that is called redshift zero, which is the contemporary universe around us. The universe was expanding and cooling down. As it cooled down, there was not much radiation there, and Sir Martin Rees coined this stage as dark ages in the history of the universe. Then the material started to collapse into stars and to black holes, and you see it here. These are the black holes, but also stars, which we call population 3 for historical reasons. So the universe was cooling down, but the stars and the black holes pumped energy in this universe, and it started to heat up. At redshift 6, which is approximately this region, the universe became transparent, and so the photons, the electromagnetic radiation, could cross it from the end to end, and then the galaxies can be observed. Okay, so why we are interested in AGN? The brightest of AGN, the active galactic nuclei, are called quasars. And you can see on the right the image of a night sky. Each point here is a galaxy, mostly of the Milky Way, I'm sorry, most of them are stars, actually, of the Milky Way. And a quasar, I pointed here as you see, with an arrow, it is not very visible, not very prominent object, but it is the most enigmatic and the most interesting object. And the only reason why it is not so luminous, because it is at high distances from us. On the left, you have a table. Redshift 6 is approximately 1 billion years after the birth of the universe. And we know about 60 quasars with the black holes of 1 billion solar masses by that time formed. Redshift 5, which is slightly more than 1 billion year in the age of the universe, we see already hundreds of them. Redshift 7, which is like 750 million years after the birth of the universe, few black holes and few quasars. And lately we found even objects, black holes, of which are which been formed less than 450 million years after the birth of the universe. And their masses I would take with the grain of salt. They may be more massive than it is written here. Okay, so quasars. What is the main point of our discussion, or what I call $1,000 issue? And that is how to form billion solar masses black holes only 500 million years after the Big Bang. In the universe, first of all, form small objects. They merge and they grow, but how can such a massive black holes form so close to the Big Bang? This is a big puzzle, and that's what scientists today try to answer. In 1984, Sir Martin Rees, who is and still is at the University of Cambridge in England, plotted this diagram without moving objects, how the supermassive black hole seeds, how did they form? And this is very complicated diagram. And over the last 40 years, we found out that most of the passes are obsolete. And the most interesting one, as we will see, is on the left. When you start with a cloud of cold gas, a very massive cloud, which starts a gravitational collapse and directly forms a black hole. So, as we say, the devil is in the details, and we are going to follow the devil in these details. How to make these supermassive black hole seeds? And the seeds, I mean, they've been initially not so massive, and then after they formed, they started to grow. The first possibility is that there is a stellar cluster, a bunch of stars, maybe 1 million stars, that merge, collapse, and form a black hole. We really don't believe that this can happen, because we tried to explain formation of black holes so early in the age of the universe, but forming a stellar cluster of million stars probably even more difficult. So I would say that this is probably not the path to the black holes. So we want in all these cases find how to make the black hole seed. So I said already excluded the stellar cluster. The next one, the population 3 stars. These are stars which formed purely from hydrogen and helium, the chemical composition of the universe. But there are only few of them in the universe. And as we will see in a moment, it takes too long a time for them to form as well. The next point are the supermassive star, meaning like a regular star, but its mass is not like a sun, not like few tenths of the sun, but maybe 100,000 to 10 million solar masses. Nobody knows such stars. They've been never discovered, but theoretically we must consider that maybe this is the way the black hole will form through the supermassive black hole, a supermassive star, and then something happens to the supermassive star, which we will discuss, and then the black hole forms inside it. And then the Martin Rees idea about simply a collapse of a giant cloud, we call it direct collapse to supermassive black hole. So all three are a big question. So I will try to rule out the population of population 3 stars. So we cannot do much by hand waving. We need to do math. Math is very complicated here. So we do numerical simulations on computer, supercomputer. What you see on the right is basically the distribution of dark matter. The nature of dark matter is not even known to us, but we know that about 80–85% of the matter in the universe is dark matter, which doesn't interact with light. And what is interesting to us, when the universe initially is uniform and isotropic, after some time, because of gravity, there is a collapse and the universe becomes inhomogeneous, and you see here the filaments, these spaghetti type features, and voids. Okay, that's like a puffed up soap bubbles. So what is important here is that if you see on the right in my blue box, that is where the dark matter forms what we call dark matter halos. And inside these halos, galaxies form. Why do they stream? Why the gas streams into the dark matter? Because if you look on the upper left, it is like a well, like a potential well, and initially made with dark matter, and the gas is streaming it because it's cold and it wants to accumulate at the lowest point of this potential well. So the dark matter is responsible for structure in the universe, and the gas is basically enslaved by the dark matter. Now let us zoom in into the blue box. Here you see that you can see the shape of dark matter halo, not yet of the galaxy. The scale here is about 20 kiloparsec. This is about the size of our galaxy, but that was very early in the age of the universe. And then if I continue to zoom in, you see dark matter on scale of 1 kiloparsec. That's a typical scale where the gas started to flow to collapse into the dark matter halo. Okay? And we will see what happens after this. Now, when something is growing, whether this is a kid or black hole, the consumption of food is very important. Too little food is bad, but I will argue that too much food is even worse. That was first realized by the person that you see here, and I will name him in a moment. His name is Eddington, and he also answered why the universe regulates how quickly the objects form. So unfortunately, or fortunately, every mother knows that if she feeds a child, a small child, then if too much food comes into his mouth, most of it goes on the floor. What happens here is, if you see on the sketch on the left, is if we take a proton, the proton, which has always electron in neighbor, and it is attracted to the black hole or to any object to the center. But if the object is luminous, that radiation tries to push it out. When the two forces, which are opposite in direction, when they become equal, you cannot fall on the object because the radiation pulls you out. And this depends only on the mass. We talk about black hole. So the black hole, I have this with the bullet, the white bullet, but that's the symbol of black hole. So for the black hole of 10 to the 9 solar masses, we get about 10 with 47 ergs per second. Erg is kind of a penny of energy. The black hole doubles its mass every 50 million years. The meaning of this is that the black hole grows exponentially. But if we start with the 20 solar masses black hole, then to get to 2 billion solar masses black hole takes about 1 billion year. But we see these quasars already 450 million years after Big Bang. So this is too long. We need to find a way which is much faster. So how quickly the black hole and stars grow? Well, if these are normal stars like the sun, which forms from the gas of 10 to 100 degrees Kelvin, they grow at the rate of 10 to the minus 5 to 10 to the 4 solar masses per year. Population 3 stars, these are the early stars in the universe. The gas is hotter at that time, and they form at a speed of about 10 times faster. But the direct collapse, that's what Martin Rees envisioned. The gas is much hotter, larger than 10 to the 4 degrees, and they eat at more than 0.1 solar masses per year, which is much faster than what we see here. That is why it is attractive to us. Now, what is the problem with population 3 stars? What you see here on the x-axis is the time. The redshift 25 is close to the beginning of the universe. The redshift 0 is today. So if we go down to redshift 7, we see already black holes of 10 to the 7 solar masses, 10 to the 9 solar masses. That is 1 billion solar masses. But what you see, these circles that I put, if the growth of the black hole is limited by Eddington law, then at redshift 7, we can only get 10 to the 7, 10 million solar masses in black hole. This is not enough. So we need to abandon. These black holes can still form, but these are not the big black holes that we discuss in quasars. So I take away, this is the same diagram that I showed you, and I take away the population 3 stars. They're simply the growth of billion mass, stellar mass black hole is too slow if we choose this path. So we have either supermassive star or direct collapse. Okay, so let's investigate these two options. So how to proceed? Well, again, we have cosmological simulations. The top line, the top row, is on scales of 1 kiloparsec. So that is basically the size of dark matter halos where direct collapse happens. What you see the colors is the colors of the gas, the density of the gas. So we skip discussing dark matter because it will simply contaminate this figure. So we go down one line, and that is 1,000, zooming in 1,000 times. So this is 1 parsec. You see the gas continues the collapse and becomes dense at the center. Then we increase by factor of 100, and we start formation of kind of elongated feature, which ultimately will form a disk. A disk will form simply because of the spin of the gas, and that will happen even before the black hole forms. So what you see here is how the gas collapsing on the way to make the black hole seed. For comparison, let me tell you that the solar system size is 10 to the minus 5 of a parsec. So we are here at the last line, we are about on scale of 10 times the solar system. This is still too much, too large compared to the size of the black hole that will form. Now, so we talk about the gravitational collapse, and there are 2 options at this point to discuss. One is that the collapse has a spherical symmetry. So it's like a sphere which shrinks. And so the spin is not important in such a gas. This is rather unrealistic situation from what we know what happens in this universe. The other possibility that there is a spin, and as a result, the gas will form a disk-like. So it will finally be stopped by centrifugal forces. Okay, like when you turn rapidly with your car or a bike, you are thrown out of the car if the door is open. That's the centrifugal forces. So a disk on the right and a sphere on the left. So on the left, you see there is no preferred direction. And as the gas collapsing, not only it reminds us about of a sphere, but it heats up. Heats up means the radiation, it wants to cool, and the photons want to escape. But where they can escape is if they are trapped in the sphere. That is a problem. So that can stop the collapse until the photons escape. On the other hand, on the right, you see formation of the disk that I cut a slice, the rotation axis in the middle, and you have a slice of the disk on the left and on the right. Here, the photons can escape up along the rotation axis, and we get what we call accretion disk with funnels where the photons escape. So the big question now is what we should choose, left or right, and what the numerical simulation tell us, and what are the corollaries of spherical collapse versus disk-like collapse. So here is a simple diagram. On the y-axis, density, volume density. On the x-axis, the distance. So this is in log. So on the right here, we have 100 parsec, 10 parsec, 1 parsec, and here on the left, it's close to the black hole. So as the gas is collapsing, initially, it will be a spherical collapse. You see the gas here, which is more or less spherical. As it collapses inside 10 parsec, it forms a disk, which you see a disk face on. And if you continue the collapse, the disk breaks its axial symmetry and forms what we call a gaseous bar. Why it is important? It is important because if we have such a bar, then the gravity, or we call it gravitational torques, the same torques that bring up water in the oceans and the up and down, the same torques will slow down the rotation of the matter, which will allow the gas to continue the collapse. So gravitational torques help to drive a runaway gas collapse. Otherwise, if it would be spherical, the photons would stop it. So let us proceed. So we have spherical collapse on the left, disk-like collapse on the right. There is no black hole yet. Everything is pre-formation of black holes, just before. So if we have a spherical collapse, under certain conditions, the gas can continue collapse and drag the photons inwards. Yes, the gravity is very strong, and it can even overcome the gravitational pull. So, but the collapse will slow down, and that is a problem. While on the right, the disk will form, and as I said before, it can cool down by allowing the photon to escape along the rotation axis. So here is a sketch, our dilemma. On the left, we get a supermassive star, which is supported by the pressure of the photons that won't escape. We call it supermassive star because it's very massive, 1,000,000 solar masses. And I call it in short SMS. On the right, we have accretion disk, not yet black hole at the center, so it's self-gravitating, it's producing its own gravity, and it can create outflows. You see the funnel where the photons can escape along the rotation axis up or down, and that is the dilemma. Which one will form? What are numerical simulations tell us? So a spherical collapse is basically what I call a star-like spherical accretion flow, no spin. The angular momentum or the spin is unimportant. The photons are trapped. And then when it becomes very hot at the center, thermonuclear reactions form when the temperature increases above 1,000,000 degrees. And we have what is called a supermassive star with a core between 10 to 10,000 solar masses. That's where thermonuclear reactions form. And that is a very interesting point. What happens next? The supermassive star has been actually discussed already 50 years ago. And scientists realized that they will burn hydrogen into helium. And it takes about 1,000,000 years, as you see here. They will be supported by radiation pressure. But at that time, nobody took it seriously that such objects can form. And I repeat, until today, we don't know that they actually exist in the universe. But now what I called quasi-star, or this is supermassive star, which starts to burn hydrogen into helium, so thermonuclear reactions. When all the hydrogen is burned, then the core of such a star will collapse and form a black hole. I would make it or display it in a particular way. So we have a star, supermassive star, with a black hole in the middle. The mass of the star is much larger than that of the black hole, and that is quite unfortunate. But because all the gas, all the envelope of the star is so close to the black hole, an interesting effect can happen. This black hole can grow faster than the Eddington law allows it to grow. Here is Eddington again, and I would say if a black hole is formed, I call it a baby because it has very small mass. How to feed it? Can we overcome? Can we feed it faster than the Professor Eddington told us it can happen? And in fact, we found out, and numerical simulations tell us, yes, this is possible. So you can literally push the food into the mouth of a child. I don't know how it will feel it, but that is what we call a hyper accretion. Okay, so in principle that can happen, but nobody yet simulated in any numerical simulations. What we did is we looked on a cloud of gas that is collapsing with the size of one astronomical unit, which is about distance between Earth and the Sun. And so the time scale is from left to right. So you see initially it is more spheroidal, then it becomes more a disk, and a channel for the radiation transfer and escape is forming along the rotation axis, which is vertical. So the radiation indeed can escape. This we know for about 6 years. What can happen next? Well, the accretion disk here is this colored, what I call the accretion disk. And when the photons want to escape, they push some of the material from the disk, and if this is supermassive star, and forms a bubble which is expanding and interacting with the accretion flow. It's a very complex situation, very difficult to solve. We tried to do something, and you see that the disk here is edge on, and the vertical arrows are the escape velocities of material. And if you look on the second row, you see the formation of empty bubble. You see it's black. The color is the density. And this bubble is indeed expanding and becoming, and the gas inside the bubble is very hot. The color at the bottom is the temperature of this bubble. So what can we say? Well, that is one pass. If we bring in something that is very important, and that is magnetic forces, then I want to show you the numerical simulations at the top, where you have a formation of a disk without magnetic forces. And you see the gas is fragmenting into pieces. So it forms stars. If it forms stars, the black hole that will form in the middle will starve, because much of the stuff will go into stars. On the other hand, if we have magnetic forces, then there is no fragmentation, no stars form, and everything goes into black hole. But whether this black hole forms or not, this is still a question. These are the details of how the black hole, towards the black hole, how the material evolves. We have no time to talk about this, but at the top we see a disk face on around a supermassive black hole supermassive star in the middle. At the bottom, you see the same disk edge on, and the color is the strength of the magnetic forces. So you see they become very strong, and so they can compete with gravity and with radiation, and that is where the problem lies. That is probably the last slide before conclusion. You see this disk edge on here. It is, I zoomed in, and you see, as I said, edge on, the arrows that you see here is direction of the magnetic forces. So on the left, this is early evolution. In the middle is you see that there is a region which there is almost no magnetic forces. They separate. That is the region. And on the right, you see that the magnetic forces are directed and forms two outflows we call two relativistic jets, and the material can escape there. Well, that is where the state of the art sits today, and I want to come to conclusions. The direct collapse of gas within 10 to the 8 solar masses dark matter halos can in principle form supermassive black holes. But the problem is we don't know how quickly the gas gets out of its spin. So either quasi-star with core collapse and small black hole in the middle, which will grow at hyper Eddington rate, or a disk, open issues. The direct collapse can naturally explain why there are no intermediate mass black holes, because in dark matter halos, about 16% is gas, and this 16% is somewhere a few times 10 to the 6 solar masses. So that naturally explains that all this gas collapses and forms supermassive black holes, and that can be maybe detected. And the last point is that if we go to the disk intermediate stage instead of supermassive star, we can we can avoid the thermonuclear phase, thermonuclear reactions. Why it is good? Well, because it slows down everything for 1 million years, and we need that this happen, the black hole will form as fast as possible. So the $100 question is written at the bottom. These objects, before the supermassive black hole forms at the center, are these objects detectable with, say, the modern telescopes? And we think it is possible, but this is a matter of observers. To finish it on the slightly lighter note, I have two alternatives how the black holes can form, and two alternative views on the black hole formation. I especially like the top one, but some people prefer the bottom. Okay, so you can decide by yourself which path you like most. That's all. Thank you very much.
Dr. Schlossman, that was absolutely wonderful. So first off, I'd just like to thank you, and I particularly enjoy this last slide that you have with alternative views or theories on massive black hole formation. So at this time, any of our concurrent viewers, if you have any questions for Dr. Schlossman, you may enter that into our live chat and we'll get you some answers. Also, Dr. Schlossman, while we're waiting for questions within our live chat, I'm sure myself as well as Dr. Stapleton have some questions for you. So if that's okay, we could go ahead and ask those.
Of course.
So to first off, to reiterate largely, correct me if I'm wrong, a main point or takeaway from your talk this evening, considering a leading possibility for the formation of supermassive black holes, you discussed direct collapse to supermassive black holes, and you discussed that direct collapse could be in somewhat of a spherical symmetry or a disk-like collapse. And it seemed, again, you may correct me, that you did lean more so towards a disk-like collapse. Now, just to briefly
It's a
explain.
personal preference, but I didn't neglect the other side. It's still possible. Yes, please go on.
Yes, of course. Just to briefly touch on things that you mentioned for each of those. So you mentioned if the collapse were to have a spherical symmetry, that the spin or the angular momentum would not be important. And you also mentioned that there would be no preferred direction for photon leakage and that photons would halt gaseous collapse and that ultimately you would have some formation of thermonuclear reactions. Could you possibly briefly expand a bit more on those thermonuclear reactions that would form?
Yes. Basically, this is a structure of any star. We have a core, and we call it thermonuclear furnace. That's where hydrogen is converted into helium, like in our sun. But we have other stars which are evolved for a longer time or more massive than the sun, and they burn helium into carbon, and carbon more burns into oxygen, and so on. And let me stress that every single atom, carbon and oxygen, and I don't need to overemphasize how important they are for our life, they formed inside these thermonuclear furnaces and been thrown out in the supernova when the star was exploding. Now, supermassive stars do not explode. The gravity is too strong to keep them, but they implode and form a seed black hole. When does it happen? It happens when they burn all the hydrogen into helium, and it is too cold for the helium to burn, so the core is collapsed, and a very special type of particles called neutrini escape from the center, and they basically cool down the center of the star. These neutrini are very strange particles. If we fill up with iron all the distance between Earth and the sun, this particle will go through this iron slab very much like a knife through the warm butter. They don't care. They're very ignorant particles. And so they can, by escaping, they take energy and they cool the center of the star, which will form the black hole as a result.
And then to touch on, again, the other possibility, with the exception of the spherical symmetry, would be the disk-like collapse, which does, as based on your talk, in my personal opinion, possibly maintain a bit more validity as far as the photons not so much halting that gaseous collapse, correct? So with the disk-like collapse, you explained how photons, there's an enabling of an escape upwards along the rotational axis, correct? And you talked
Yes,
about how the gravitational torque slow down such a rotation of the matter, and this allows for there to be some kind of gaseous collapse, correct?
yes.
So in that sense, there does seem to be
You absolutely marvelously did it in few lines that I spent 45 minutes on.
So in that sense, just one of my questions, which you have answered, it seems, throughout your answer now and your talk, is that there does seem to be, maybe you could say, some more validity associated with a disk-like symmetry as compared to spherical.
Yeah, well,
Possibly.
the disk symmetry naturally allows for escape in the vertical direction. There is escape route for photons. Now, the interesting point that when these photons escape, they also drag some of the material from the disk and forms these two collimated jets. And the magnetic force helped to collimate them. And they look more like a laser pointers, much more complex that we use in our classrooms, because these jets can propagate to 1 megaparsec, which is about 10,000 times larger. No, I would say 100 times larger than the size of the Milky Way, and they stay collimated. While if we would use our laser pointers, we definitely cannot signal even to the nearby star. It will be completely decollimated. So nature knows somehow how to collimate these jets, and that is probably using magnetic forces. This also brings us to what is called, what people tried for the last 70 years, to build a thermonuclear furnace on Earth and get a free energy out of this, converting hydrogen into helium. Our problem is that because the temperature is about more than 1 million degrees, we need to put this material where the thermonuclear reactions are inside a bottle. But everything will be vaporized at 1 million degrees. So we want to construct magnetic bottles. But our bottles, magnetic bottles, are leaky. They are destroyed in less than 1 second. So billions of dollars been spent on this, and we still don't know how to do it. But as a Nobel laureate of 2003, Professor Vitaly Ginzburg, who is one of the fathers of Soviet atomic bomb, on visiting me here in Lexington, and we discussed this subject, and then we went for lunch. We went outside the building, and he said beforehand, he said that he doesn't believe that we will build thermonuclear furnace on Earth. Too expensive. And if we will build, then it will go directly to museum. But then we went out of the building and he looked on the sun. He said, here is the solution. There is a thermonuclear furnace inside the sun, but we cannot reproduce it.
I think that's absolutely fascinating. Dr. Stapleton, do you have any questions?
Yes, I just wanted to ask, so many times we talk to students who are interested in either math or physics, and I just wanted to know, what advice would you perhaps give students who are interested in pursuing physics as a career or as a degree option? Any advice that you could give them?
Oh, many advices. The question is, what is the most important one? Pay attention to math even in high school, and if you can, even earlier. We know that we can teach math even to 2-year-old kids if we know how to communicate with them. Teaching physics is much more difficult. There should be additional experience in life. But then, if you are not afraid of math, and if you like biology and maybe physics in high school, then you're welcome to come as an undergraduate to university. We have 600 universities in this country. Each one is teaching physics. And we have physics classes. And some student told me, I never believed that I will study physics. We didn't have physics teacher. Many high schools don't have physics teacher, unfortunately. And find yourself a physics teacher, even in high school. And then nothing to be afraid. It's fun. It's hard work, but it's also fun.
Thank you so much. I think that's really meaningful for students to hear, that, math and science and physics and biology, all of those can be fun, and are great pathways to, lifelong learning, whether it's the astronomy club or whether it's a career, what have you. So we're really excited that you came to speak to us today. I really enjoyed your talk. Thank you.
Thank you very much. Thank you for invitation again. Bye.